Okay, in this video I'm going to finally get around to the purpose of this tutorial series on complex analysis. Specifically, I'm going to evaluate the Planck integral. As usual, I'd like to draw your attention to my website, universityphysicstutorials.com. Here I have all my videos archived and listed, and I have a few other bits and pieces which may be of interest to you. Before we begin, let's look at the previous videos in this section and those relevant to this section. We're discussing complex analysis, and therefore the videos on complex numbers are relevant and important. Then in the section on complex analysis, I derived the Cauchy-Riemann equations, Green's theorem, and the divergence theorem. In video number 5, I looked at the relationship between the two theorems, Green's and the divergence theorem. Video 6, I introduced the Cauchy integral theorem. Thereafter, we looked at the differential arc length formula and derived the Cauchy integral formula. That allowed us to derive the Taylor series and the Lorentz series expansions. Finally then, in video number 10, I discussed the residue theorem. This is by far and away the most important result of the series on complex analysis thus far. It's in actual fact the residue theorem which allows us to evaluate the Planck integral. In addition to the videos on complex analysis, thermodynamics video number 15 is important. In that particular video I took the Maclaurin series expansion of cosine of x, and in this video we're going to need the Maclaurin series expansion of sine of x. Of course they're very similar, and the video number 15 will show you how to do that. I would like to give you a reference, and it's to a book written by Erwin Kreutzig, and it's Advanced Engineering Mathematics. Specifically to chapter 15, where towards the end of it he discusses integrating a function sine x over x between 0 and infinity. To be honest, that's pretty much what we're going to do in this video here. So if you understand what Kreutzig has done, well then most likely you will understand what is required in order to evaluate the Planck integral. I need to be honest and upfront with you in regard to the difficulty of this particular derivation. There is a health warning associated with this particular process. The only other video in my tutorial series thus far which I associated a health warning with is the derivation of the Laplacian in spherical coordinates. The sort of person who I expect to get maximum benefit out of this current video is a person with pretty strong mathematics. Perhaps they are doing postgraduate work at the moment, or they're a particularly strong undergraduate student. Is a person who is very... The other sort of person who might get good mileage out of this is the sort of person who really wants to know all of the background mathematics in order to get at their physics properly. My advice, if that is the case, is that you strike a balance between going down what is quite a significant mathematical tangent and the payoff you'll get in terms of understanding your physics. There's definitely a balance to be struck somewhere. To be honest, evaluating the Planck integral isn't particularly difficult. What it does require, however, is a knowledge of lots of different areas in mathematics, the most important of which, of course, is complex analysis. And that's why I have had 10 previous videos in this section to build up the necessary skills required in order for us to address this particular integral. Before I begin, I'd like to make a note about the numbering of this particular video. In a previous life, this video was number 9 in the series on complex analysis. However, it currently is placed at number 11. I've made a note to that effect clearly at the start of the video. However, later on during the video you will see reference to complex analysis video number 9 as being for the Planck integral. I'm sure that won't cause any confusion, but I would just like to apologize in advance. Okay, in this video I would like to continue on with my tutorial series on complex analysis. This is video number 9, and specifically I'm going to finally get around and derive the Planck integral. I'd like to draw your attention to my website, universityphysicstutorials.com. Here I have all my videos archived and listed, and I have a few other bits and pieces which may be of interest to you. Before we begin, I'd like to remind you of the previous videos in this section and other relevant videos. We are of course discussing complex analysis, so it's good to know about complex numbers. In the series on complex analysis, I discussed the Cauchy-Riemann equations. I showed you two derivations of Green's theorem and later one of the divergence theorem. I linked and showed the relationship between Green's theorem and the divergence theorem, and thereafter derived the residue theorem, probably the most important result of the lot. Video 7, the differential arc length formula, is related to video 6, and I suppose I put it all together by using the Lorentz series expansion, which is another way really of looking at the residue theorem. In order to derive the Planck integral, we're going to need the Maclaurin series expansion for sine of x, and in thermodynamics video number 15 I did the Maclaurin series expansion for cosine of x. I need to be honest and be upfront in regard to the difficulty of this derivation. There is a major health warning associated with it. The only other video so far which I've associated a health warning with is the derivation of the Laplacian in spherical coordinates. The sort of person who I'd expect to get maximum benefit out of this video is a person who's got pretty strong mathematics. Perhaps they may even have finished their undergraduate education or doing postgraduate work, or they're, like I said, a particularly strong undergraduate student. The other sort of person who might get good mileage out of this video is a person who is very keen on getting to know all the background maths in order to give their study of physics and later quantum mechanics the best shot possible. Actually deriving the result of the Planck integral isn't that difficult, but what it requires is the utility of lots of other results from mathematics, and a lot of it is complex analysis. That's actually what makes it most difficult, because it involves lots of different other areas of mathematics, and it isn't, for example, just a result of complex analysis. It requires, for example, power series and other things like that. One of the first topics which a student being introduced to quantum mechanics will study is blackbody radiation. This is the study of the electromagnetic radiation being emitted and absorbed by a black body. This was first done in about 1900 by Max Planck. It was about this time that the concept of quantization of energy came about, and Max Planck was central to this new development, this new concept, with the study of blackbody radiation. Building upon Planck's law, we come to the Stefan-Boltzmann law. This basically describes the total irradiance of an object. I is equal to sigma t to the fourth. In order to derive this particular expression, we come across the Planck integral, and I've written the Planck integral on the top right hand side of your screen. Now, I don't want to get bogged down in this. We have a heap of constants at the left hand side, and I've done a change of variables from x to u, and the integral we're really looking at here is the integral from 0 to infinity of u cubed divided by e to the u minus 1 integrated du. Personally, when I began studying quantum mechanics and I was introduced to the blackbody radiation, I wondered how we could do this. I wondered how was this integral performed. I thought perhaps that it was done in a manner that would be similar to getting the Gaussian integrals. Of course, doing that got me absolutely nowhere, and I spent many hours, wasted many hours looking at this particular integral. It would be normal, I would suggest, for an undergraduate lecturer to gloss over the actual calculation or derivation of this particular integral and just take its result, which by the way is pi to the 4 over 15. This is something which wouldn't have gone down very well with me. I'd like to know where these things come from. But to be honest, I can understand why lecturers will do that. The reason is because the physics is the most important thing in an undergraduate quantum mechanics class, and it takes reasonably complicated mathematics to do it. So there's a bit of a balance to be struck between understanding the mathematics and using the result of the complicated mathematics in order to get the physics. So the Planck integral is written in green in the center of your screen, and I've done a change of variables from u to j. So we integrate from 0 to infinity of j cubed e to the j minus 1 dj. I'm going to call this integral capital J, and as I'm sure you have seen in the past, it's pi to the 4 over 15. I am regularly taken aback at the simplicity of this result and other results like with the Gaussian integrals. I think it's absolutely amazing. And after the next couple of minutes, and you'll see how this is actually derived, you'll hopefully be very impressed at the simplicity of the result. So let's get going. This particular integral is very difficult to get at. So what we do is we consider a separate but related integral, and later on we will be able to get the result for the integral capital J. What we do is, instead of using just capital J cubed up top, we actually change it and we look at the integral, which I'm going to call capital F of k, whereby we replace j cubed and insert the sign of the constant k times j. Everything else is the same. This of course is an odd integral because sine is an odd function. It's symmetric around the origin. Now we come to the first inclusion of other areas of mathematics in order to solve this, outside of complex analysis I mean, and that's power series. So we need to look at the Maclaurin series expansion of the sine of x. The Maclaurin series basically says that we center the expansion around x is equal to 0. And I've written the Maclaurin expansion of sine of x there. However, just in case you're not convinced, I've written the formula for the Maclaurin series expansion here on the right hand side of your screen in black. In order to calculate the coefficients, the a sub n's, we need to get the derivatives of our function sine k j, or sine kx. So you have the 0th derivative, the 1st, the 2nd, the 3rd, and so on off up until infinity. We must evaluate each of these at x is equal to 0, and we get 0 k cubed, and so on. Putting them all together using the formula here, we get the expression second from bottom on your screen. Putting this more compactly, we get the Maclaurin series expansion of sine of x. We're going to insert this back into our function capital F of k and move on from there. So taking the first three terms of this, of course, infinite expansion, we say that capital F of k is approximately the integral from 0 to infinity, k sub j minus kj to be cubed divided by 3 factorial plus kj to the 5th divided by 5 factorial, all divided by e to the j minus 1 integrated dj. Of course, we can instead write this as the sum of three different integrals, and I've written those there in the center of your screen in green. And notice we have our coefficients. We have a sub 1, a sub 3, a sub 5. Of course, the even coefficients turn out to be 0. I hope you can follow me so far. We just made a Maclaurin series expansion. We only have the odd coefficients, and instead of writing the integral as 1, we write it as 3. And the reason we write it this way is because we're able to incorporate the original integral capital J. The original integral is here. So we have j cubed over e to the j minus 1. By writing capital F of k in this manner here, we were able to relate each of these sections to our original integral capital J. This I do at the bottom of your screen. You might ask yourself, how is it ever going to help us? Why is it useful? Well, if we expand both sides of this particular expression in powers of k, we're able to see that the integral j, although it's obviously here and here as well, but the simpler one is the center expression, which I've now highlighted. We can see that j is minus 6 times the coefficient on the k cubed term. What we seek to do is find a closed form of capital F of k and compare it to the Maclaurin expansion of capital F of k above. Now you might be saying to yourself, what on earth does that mean? It means this. We take what is written on the right hand side of here as fixed, and we don't look at this for the next while. Instead, we go back to our capital F of k, and we see if there's another way of writing this. Is there another thing we can do which we can later expand in powers of k? So let's say we get something capital F of k is approximately, I don't know, let's A, B, C like this, where this was the coefficient k, this is the coefficient k cubed, and this is the coefficient k fifth. Well, since these are equal, what we'll be able to do is knock out these terms because they are irrelevant and compare what would be the coefficient b with this, and we'll be able to get the integral j. Remember, we're looking for j, so we're going to get the expansion and take the coefficient of k cubed from f of k and compare them. Now you ask yourself, how are we going to ever evaluate capital F of k? Well, let's begin. Well, in the center of your screen is capital F of k. We note, of course, that there is a sign on the top, sign kj. Now, the problem with this integral and what makes it so difficult is the denominator. The denominator has what's known as a singularity, a divide by zero scenario. That's actually what makes this really difficult. It means that it's not analytic. In other words, it's not defined at that particular point. It doesn't have, you can't get the derivative. So what we're going to do is we're going to integrate around the pole or the singularity, and we're going to basically employ the residue theorem. Now, in order to do this, it's often easier to consider, instead of sine kj, let's employ Euler's equation. Euler's equation says e to the x is cos x plus I times the sine of x. And what we're going to do is, while we went from j over here to sine kj, now we're actually going to go to e to the kj. And I shall discuss that more in depth right now. So on the bottom of your screen, we're going to consider capital F of k. Now ignore this limit for the moment here. So it's the limit, let's say from, I said ignore the limit, it's going to be the integral from, let's say, 0 to infinity of e to the k z dz over e to the z minus 1. Now you might be asking yourself, well, hold up a second, why is after making another change of variables? Well, the reason is this. We're going to be using complex numbers. We're going to be working in the complex plane, and it's customary for us to use the placeholder z. Now, it's perhaps a bit unfortunate that I used the placeholder j above, because j was just, it happened to be our placeholder. But in the complex plane, we know that z is equal to x plus I times y. And I'd like to make, or to avoid any confusion between the j hat unit vector, for example, and the dummy variable small j that we were using. So in transforming the integral capital F of k from having a sine kj on top, what I'm going to do is I'm going to actually change the variable from j to z like this, and I'm going to invoke Euler's equation, so we get e to the I kz, where of course e to the I kz is cos kz plus I times sine of kz, and we're thereafter we're going to take the imaginary component of e to the I kz, because the imaginary component of that is simply sine kz or sine kj. I hope you're following me. I know that there seems to be a lot of dancing around being done here, but it'll become clear later on why I'm being so fastidious in this regard. Now, as I said earlier on, this expression has a pole when e to the j or e to the z is equal to 0. So at the point 0, this will blow up. So we can't integrate from 0 to infinity, but rather we integrate from a point slightly away from 0. We call that point epsilon. And what we do is we take the limit of our integral as epsilon goes to 0, and that will allow us to get at the integral capital J. So just once more to recap, we want to calculate j, but that's quite difficult. We went from the integral capital J. We substituted, instead of having small j to be cubed, we went instead and we're going to consider sine kj. And then what we did was we invoked Euler's equation, where we have cos plus I times sine. And we're going to analyze this new integral, and at the very end take the imaginary component, which will correspond to sine kj. Because we're dealing with complex numbers, it's customary to use the placeholder z, and that's what I'm going to do. Finally, there's a pole at the point z is equal to 0, so we can't integrate from 0 to infinity, but rather we go to a point slightly away from it, which we call epsilon, and we take the limit as epsilon goes to 0. If you're not sure why the pole is at z is equal to 0, then you can pause the video and check out this section here. The next thing we need to think about is, how do we make this integral become infinite? How do we extend it to infinity? We have this particular integral here. Now, obviously, there are lots of suggestions that you could make in how to do this. The best one is the following. Let's consider yet another new or changed integral. Let's consider f prime of k. And what we're going to do now is consider a closed contour integral, where we extend z, the radius of our closed contour integral, to infinity. Of course, we thereafter get our infinite integral. Now, what does this look like? Well, if you've seen contour integration in the past, you'll know it's all about selecting a contour, which makes the integration easier. So the difficult thing we have to do now is actually select this particular contour. What are we going to use? Now, if you consider the contour which I'm going to show you, I'm sure you'll be quickly convinced of its utility. So remember, it's not easy to integrate from 0 to infinity, especially with this pole at z is equal to 0. So we're going to consider a contour, a closed loop somewhere of some form, and we're going to extend this contour to infinity, and this should give us the result we're looking for. Just to remind us, the integral is usually presented as one of x, where I present it as one of j, and this is because we're going to be doing some complex analysis, and they have z is equal to x plus I times y, and although j and x are really the same thing, I would like to use j as my dummy variable. So if you're looking at some other authors, they may have x. I'm using j. It's no big deal. So let's consider the contour in pink drawn in front of you. So we have, first of all, we have our x-axis. This is the real axis. We have our imaginary axis here, the y-axis. We have our pole at z is equal to 0. But we also have a pole at z is equal to twice pi I. That's what I said you could see when you paused the video a couple of minutes ago. So what we're going to do is we're going to consider a contour which goes from, we'll say, x is equal to epsilon, y is equal to 0, which is this point. It goes to x is equal to or a radius, y is equal to 0, this point. It goes up to x is equal to or, y is equal to twice pi I. It moves over just away from the other pole to x is equal to epsilon, y is equal to twice pi I. It drops down towards the first pole. Excuse me, it doesn't do that yet. It goes to this point here, which is x is equal to 0, y is equal to twice pi I minus epsilon I. It drops down towards the first pole, which is here, at x is equal to 0, y is equal to epsilon I, and back around. And what we're going to do is we're going to get this radius or length term to extend to infinity, and thereafter we're going to get the infinite integral. I think it's worthwhile for you to pause the video and just understand this particular diagram. Note the poles and where they came from and all the different points on it, because we'll be discussing each of them.